Swayam Prabha. Digital India. Educated India.
In this problem solving session, we will solve problems related to density operators mainly. So the first problem, you are asked to verify if the given matrix rho is a valid density matrix, and if so, then find the corresponding normalized state. So let us do it. We know that the matrix rho would be a valid density matrix provided it satisfies certain condition. For example, the matrix rho has to be Hermitian. Has to be satisfied. Another condition is the trace of rho has to be equal to 1 and eigenvalues of rho has to be real. Let us check one by one whether these three conditions are satisfied by the given matrix. As I see that the elements here are real, so finding rho dagger is trivial because we have to first take the complex conjugate and then take the transpose, because complex conjugate would be the same one. Then if we take the transpose, then we'll get half, minus half, minus half and half. So this is exactly the same as rho. So therefore the matrix, given matrix, is Hermitian. Secondly, trace of rho, the sum of the diagonal elements, half plus half, that is equal to 1. So this is also satisfied. Now let us find out the eigenvalues of rho. So eigenvalues of rho, to find it out, we have to set the characteristic equation. You have to set up the characteristic equation, so we can easily set it up. That would be determinant of, say, half minus lambda minus half minus half, half minus lambda, that is equal to 0. And if we solve it, we will get half minus lambda whole square minus 1 by 4 is equal to 0. Or we have lambda minus half is equal to plus minus half. So therefore what we have is lambda is equal to half plus minus half. So this is going to yield us eigenvalues lambda 1 is equal to, say, 0 and lambda 2 is equal to 1. So as you see that the eigenvalues are real. So definitely it implies that rho is a valid density matrix. Is a valid density matrix. Let me show you one thing quickly. If I find out what is rho square, so rho is half minus half minus half half. So I have to take the multiplication of this matrix twice. If I do it, as you can see, we'll get here the first term would be half, here we'll have minus half, here we'll have minus half, here we'll have a half. So rho square is equal to rho. This implies that rho represents a pure state. We are asked to find out the normalized wave function as well. So let us state vector, let us work that out. Rho we can write in terms of state vector as it is ket psi bra psi. Let us say the psi ket psi is represented by a column vector with elements a b, and bra psi would be a row vector with elements a star b star. And if we but the way this we have to equate with rho, that is your half minus half minus half. So this implies that I have from here we'll have mod a square ab star b mod b square, and this let me compare with element by element. Okay, first let me write it. So clearly it implies that mod a square is equal to half, mod b square is equal to half, and a star b or ab star is equal to minus half. So if I take a is equal to 1 by root 2, and I must have to take b as minus 1 by root 2. So therefore the state vector psi would be 1 by root 2 1 minus 1. So this is the normalized state vector. Okay, now let us work out this particular problem. This is actually, you have to find out sigma x cross sigma z. This is basically tensor product between two matrices. Just let me quickly remind you about what is tensor product. Tensor product, say we have a matrix A is an m by n matrix, B is an say p by q matrix. Okay, then tensor product of A and B is denoted as A cross B. This is the symbol for tensor product, and that would be, so we have the element for matrix A is A11, A12 and so on. So we have to, this element would be multiplied by the matrix B, and here you will have A21B, A12B. This way we will have up to A1 and B. And similarly, if you go this side in the column, we'll have A, M1B, A, M2, A, M2B, and so on. And finally here we'll have A, M and B. Okay, so this is what we have. So let us apply it for our problem. Sigma x tensor product with sigma z. We know that sigma x is represented by the matrix 0, 1, 1, 0. So this is sigma z also we know. Let me go step by step. So here I have 0 into sigma z, and then we have here 1 into sigma z. So this is here sigma z, 1 into sigma z here, sigma z, and 0 into sigma z. So what I will have, because sigma z, we know that this is 1, 0, 0, minus 1. So I will have here 0, 0, 0, 0 from this, and sigma z is 1, 0, 0, minus 1. From here I will have 1, 0, 0, minus 1, and from here I will have 0, 0, 0. So you will see we will get a 4 by for matrix. Let us now work out this problem. You are given two kth vectors and we have to find out the tensor product of these kth vectors. Let us do it. So kth u is equal to AB column vector and kth v is equal to CD. So tensor product of kth u and kth v would be, so here we have the, let me first write down the elements of u, a, b, and then we'll have here the kth vector v. So now if I write the kth vector v as well here, then I will have AC, AD, BC, BD. So this is the tensor product. In fact, many times or often U tensor product V is often abbreviated as UV. Okay, so or even as UV. Okay, now let us go to the next problem. You have to show that the tensor product of two combination of two kth vector, one is kth vector. Okay, this is your kth vector, this is your bra, this is your kth, this is bra. So you have to basically show that this would be simply equal to this one, and you are asked to take kth is as 1 0 and kte as 0 1. So let us do it. So first let me work out kz, bra e. So this would be this is the outer product. So kz is 1 0, bra e would be 0 1. So if I take the matrix multiplication, I will have 0 1 0 0. Okay, and then outer product of kt and bra z, that would be kt is 0 1 and bra z is 1 0. So therefore I will have 0 0 1 0. Okay, now let us take the tensor product or direct product. kz bra e tensor product with kte bra z, that would be just multiplication of these matrices. So let me write here 0 1 0 0 0 0 1 0. Of course this is tensor product, so therefore what we have here is 0 0 0 0 0 0 0 0. Then here we'll have 0 0 1 0 and 0 0 0 0. I think it's easy to see. Let me say this is equation number 1. Okay, now we have kz kte, actually kz kte, let me get this. kz kte would be kz is 1 0, kte is 0 1. So its tensor product would be 0 0 0 1 0 0 and kate E kate Z, the tensor product again, it is kate E is 0 1, kate Z is 1 0, so that would be 0 0 1 0. Okay, so therefore actually this I can write as abbreviation kate ZE, and here I can write it as kate EZ. Now the tensor product of kate ZE and bra EZ, that would be kate ZE we have worked out, and that is 0 1 0 0, and this is would be the row vector EZ. Kate EZ we know, so bra EZ would be 0 0 1 0. So if I do the maths, I will get here 0 0 0 0 0 0 1 0, because 1 is sitting there, and here I will have 0 0 0 0 0 0 0. So let me say this is my equation number 2. So if I compare 1 and 2, this is 1, and then this is my 2. If we compare both sides, both the expression 1 and 2 implies that kate Z bra E tensor product with kate E bra Z, we can write it as ZE EZ. Okay, this is actually a general result, and this result is important and it will be utilized in the next problem. Let us do this problem. You are given a state vector, a state kate, and you are asked to find out the corresponding density matrix. Then partial trace it over the first Hilbert space to find the density matrix of the second system. Okay, so as you can see from this expression for the state vector here, that this is actually a composite system. System 1 and system 2 is there, and we have to find out the density matrix for the second system by taking partial trace method. So let us do it. So we have kate psi is equal to 1 by root 2 kate Z kate E. Of course this is tensor product, right? Kate Z tensor product kate E minus kate E tensor product kate Z. Density matrix would be kate psi bra psi, and if we do that, 1 by root 2 will appear twice, so we will have half here. Let me write here kate Z kate E minus kate E kate Z tensor product with the bra psi, that would be bra Z bra E minus bra E bra Z. Let me now open it up. I can use the previous problem's result here. So this one tensor product with this one is going to give me kate Z bra Z tensor product with kate E bra E. Then this one with this one will give me kg bra e tensor product with kate e bra z. Then let me take this one with this one, so I'll have minus kate e bra z tensor product with kate z bra e, and finally let me take tensor product with this one with this one, and this will give me plus kate e bra e tensor product with kate z bra z. Okay, so this is what we have. That would be our density operator. Now to get the second system, we have to trace out first system. So the density operator for the second system would be, I have to trace out system 1. So that is simple, we know it how to do that. So that would be here half. If I take the trace here, then as you know that this is my first system, this is my second system. So if I take the first system here, it would become simply this direct product would be become now scalar product like this, and here I'll have second system would be kt bra e. Similarly for the second term, that would be I will have scalar product ze, and here kt bra z, and the third term will give me scalar product ez, and here I have kz bra e, and the last term will give me scalar product ee, and here I'll have kz bra z. And I know that these are kz and kt are orthogonal to each other, so this is normalized, this is normalized, but this is equal to 0. This is orthogonal to each other. Scalar product would give you yield 0. So I will end up with half kate e bra e plus kate z bra z. In fact, this is nothing but identity matrix. This part is identity matrix 1 0 0 1. Let us now work out this problem. This is similar to the previous one. For a system of 2 qubits in a single state is given in terms of density operator. This is the density operator for the composite system. Here the first one, this kate 0 belongs to system A, and kate 1, this is actually tensor product, it belongs to system B. Similarly here it belongs to A, and this belongs to B. Here it belongs to A, it belongs to B, this belongs to A, this belongs to B. Let us work it out. You are asked to find out the reduced density matrices for each qubit separately. So first of all, let me open up this density operator rho AB. Let me write first, it is half kate 01 plus kate 10 tensor product with bra 01 plus 1 0. If I open it up term by term, so let me take the tensor product with this one with this one. So I will have kate 0 bra 0 tensor product with kate 1 bra 1. So you see this is system A, this is system B belonging to, and similarly we have, now you take this one with this one, then we'll have gate 0 bra 1 gate 1 bra 0, and now let me take direct product with these two, then I will have gate 1 bra 0 direct product with gate 0 bra 1 plus, now let me take this one with this one, I will have gate 1 bra 1 tensor product with gate 0 bra 0. Okay, so then finding out the reduced density matrix for A would be easy. I have to just trace out B from row AB, then I will get row A, and this is system A, this is system B, similarly for all these other terms. So if I trace out B, we know we'll get, because gate 0 and gate 1 are orthogonal to each other, so if I trace out B, so this is going to be the scalar product of 1 1, so that would be 1, and here I will have gate 0 bra 0, this term would go to 0, okay, because the scalar product of 1 0 would be 0, and I will left out with finally this term. From this term I will have gate 1 bra 1. Okay, similarly you will get row B, I have to trace out A from row AB, and here I will get half gate 1 bra 1 plus gate 0 bra 0. So in fact, as you can see, I have row A is equal to row B, and that is equal to half, and as you can see, these are identity, this is identity matrix, this one also. So this is what I have. Okay, now let us work out this simple problem on harmonic oscillator. Consider the quantized simple harmonic oscillator. The Hamiltonian is given, and the annihilation operator and the creation operator are also given. Using this, you are asked to verify these 4 facts, that A dagger is equal to 1, and that is actually identity, and these relations you have to prove, and finally you have to show that the Hamiltonian can be written in this form using this annihilation and creation operator, and this is equivalent to this form, well-known form. Let us do this. So we have annihilation operator. A is 1 by square root of twice h cross m omega x cap plus ip, and A dagger is equal to 1 by square root of twice h cross m omega x cap minus ip. So from these two relations we can express what is x cap and what is p cap. X cap would be, we actually know it, that it would be square root of h cross by twice m omega, that is the 0-point fluctuation, then A plus A dagger, and P would be equal to I square root of m h cross omega by 2 A dagger minus A. Okay, now force relation A dagger, So if I put the expression for A and A dagger, then okay, I have here A is equal to m omega x cap plus IP. Then the factor of 1 by h cross m omega, let me take it outside. Here I have 1 by twice h cross m omega outside. And from A dagger I have m omega x cap minus IP, and again the factor of twice h cross m omega, let me take it out. So therefore I will have 1 divided by twice h cross m omega x cap plus IP m omega x cap minus IP. Now if I take the commutation, I know that x cap and x cap, this will get commute, they commute. Only x cap, I have to just bother about the cross terms only, these cross terms. So therefore what I will have here is 1 by twice h cross m omega. Let me write it this way. I have m omega minus I x cap p. Okay, so I'm taking this term and this term. Then I have from this term and this term, I have I m omega p cap x cap. We know the commutation relation between x cap p cap, that is equal to I h cross. So therefore I have 1 by twice h cross m omega minus I m omega I h cross, and here I have I m omega I h cross. Alright, so you can immediately see that this would be 1 by twice h cross m omega, and this one and this one would be twice h cross m omega, and this is equal to 1. Okay, this is the first part we have solved. Second one, second relation, you have to prove A dagger A. These are very trivial, but only for those who may not be familiar, I'm doing this problem is for them only. So you have A dagger A, I can write it this way, and we know that A dagger is equal to 1, so this will give me simply A. And then the third relation, you have to prove A dagger A, and here I'll have, I can write it as minus A dagger A dagger. This I can write as minus A dagger A dagger, and I know that A dagger is equal to 1, so I have here minus A dagger. And finally, in the last part of the problem, the Hamiltonian we have to express in terms of creation and annihilation operator. Hamiltonian is given as p square by twice m plus half m omega square x square. If I put the form of x and p, which is from here, x and p, if I put it here, I will get the first term would turn out to be minus h cross omega by 4. You can check it. You'll have A dagger minus A whole square plus h cross omega by 4 A plus A dagger whole square. So if you do the maths, you will get h cross omega by 2 a dagger plus a dagger a. And again, utilizing the relation a dagger is equal to 1, you can also show that h is equal to h cross omega. From here you can show that this would be a dagger a plus half. Okay, so in the next problem solving session we'll actually try to solve problems from coherent and squeeze states, as well as some problems related to quantization of electromagnetic fields.